partial derivatives here. So one application is called this linear approximation of a function of a single variable. So let's see what this linear approximation about, for a function of a single variable. I believe you have learned this before, so let's review this, and then we see the extension of the idea to a function of two variables here. So suppose we are given a curve in red here, represented by y equal to a function f of x. So this is a function of a single variable. So the graph is a curve, right? The graph is two-dimensional, and suppose it is a curve here as shown in red here. And there's a point P on the curve y equal to fx. So at the point P, we can there's a tangent. There's a line that's just tangent to the curve at the point P, as the tangent line is shown in green here. And we can also determine the slope is given by f prime, isn't it? The slope of P of the point P at the point x equal to A is equal to f prime A. Yeah, that is the slope. With the slope equal to f prime A. Okay. Prime here means derivative. The derivative of f evaluated at A. So given a point P and a slope, we can determine the equation of the tangent. And the equation is given by y equal to f of A plus f prime A times x minus A here. Okay, you can use just using additional mathematics, knowing a point and the slope, then we have a slope point formula here. So that gives rise to this equation here. And suppose there's another point Q, which is close to the point P on the curve y equal to f of x. Okay, so imagine a point Q is close to the point P here. There's a point T right above Q here. The point T is on the tangential line here, which is right above Q. And T and Q, therefore, they have the same x coordinate, x here, right? Now, think what happened as x gets closer to A. If x gets, if x moves closer and closer to A, then the point Q will move closer and closer to the point P, isn't it? And Q and T, then Q also will move closer and closer to the point T on the tangential line directly above the point Q, right? So this is what happens as point X gets closer and closer to the point A. So when X gets closer to A, notice that Q gets closer to P, and also Q will get closer to the point T. Yeah. And therefore, the y coordinate of Q here will get closer and closer to the y coordinate of T. Therefore, when x is approximately equal to A, then the f of x here, which is the y coordinate of Q, will be approximately to the y coordinate of T. And the y coordinate of T is equal to this expression here. So therefore, if x is close to A, fx is approximately f of A plus f prime of A x minus A. This is the approximation symbol here. Okay, we have the equal sign. This is the equal sign. the sign below is an approximate sign. Or the approximation symbol. Okay, approximation sign or approximation symbol here. So so again, as x, if x is approximately equal to a, then f of x is approximately equal to f of a plus f prime a times x minus a here, right? You see, when x gets very close to a, this bracket term will get very, very small. Okay, will become very, very small. So as x tends to a, if we take the limit x tends to a, then the right hand side tends to f of a. Yeah. So this is called a linear approximation formula for the function of a single variable. Yeah. Now, if I replace x by a plus delta a, okay, if I assume x is very close to a, then I can think of x as a plus a small quantity delta a. Okay, delta a is close to 0. Okay, think of delta a is small, which is close to 0. So when delta a is small, a plus delta a is close to a, right? So if I replace x in this blue box here by a plus delta a, then x minus a becomes delta a. Okay, so this is also called a linear approximation formula here. Yeah. So if I know f of a, and if I want to approximate a value of a value that is close to a, then we can use this formula to get a quick estimate here, to get a quick estimate. All right. So that's for the function approximation for a single variable. So now we extend the idea, linear approximation, for a function of two variables, z equal to say fxy. So imagine we have a curve, the graph of z equal to fxy is a surface, right? We have looked at this, we have studied this before and look at various examples that the z equal to fxy, a function of two variables, the graph is a surface in a three-dimensional space. And suppose that we have a point P on the surface here. Okay, P is a point on the surface. So P has coordinate, say A, B, F, A, B. Okay, the point P is on the surface here. And there's also a tangential plane. Okay, for a single variable, we have a tangential line. For two variables, we have a tangential plane, as shown in green here. Okay, we have a plane that just touches the point P on the surface. Yeah. So and the equation of the plane is given by this formula here. The equation of the tangential plane is the equation of the plane tangent at the point P. If P has coordinate AB, XY coordinate AB. The equation of the tangent plane is z equal to FAB plus f partial x. Okay, this is partial derivatives here. F partial x evaluated at AB times x minus a plus f partial y at the point AB times y minus b. Okay, so this is the equation of the plane, tangential plane here. So imagine we have another point Q also on the curve, on the surface. Suppose it is also close to the point P. and we have a point T directly on the tangential plane, directly above the point Q. So now what happens? Imagine what happens as XY gets closer and closer to AB. Yeah? When XY gets closer to AB, then the point Q gets closer to P. Point Q also gets closer to the point T, right? Capital T here. So therefore, the Z coordinate of Q gets closer to the Z coordinate of T. And therefore, we have this relation here, approximate relation here. Fxy is approximately for if xy is close to the point AB, then fxy is approximately equal to fab plus f partial xab times x minus a plus f partial yab times x minus b. Okay, so this is the linear approximation formula for a function of two variables here. Now it involves partial derivatives. Okay, now if I replace x by a plus delta a and replace y here by b plus delta b, assuming delta a, delta b are small, then we get this equivalent linear approximation formula here, right? And the same thing can be same idea, can be also be extended to linear approximation for a function of three variables. If w is f x y z and x y z is close to the point a b c, then we have this linear approximation formula for a function of three variables. Or in this the equivalent form. Okay, where I have replaced x by a plus delta a, replace y by b plus delta b, and replace z by c plus delta c. All right. So these are called linear approximation formulas. Yeah. Okay, let's see some example. Let's see some example. Yeah, the next thing is the concept differential. Okay, I'll discuss this after looking at, let's see one example first. Let me pick one question from sample test 1B. Sample test 1B, is it this one? Ah, yes. This is a sample test question. Which is related to electricity. Yeah. The power P consumed by a resistor R and voltage E is given by P equal to E cube over square root R. Is it true? You are in the faculty, School of Electric. Is it true?
Not sure. Maybe.
Not sure. Maybe you haven't studied this yet. The power P consumed by a resistor R and voltage E is given by P equal to E cube over square root R. All right. So here P is a function of P is a function of two variable E and R. Yeah. Given that E equal to 10 volts and R is 2000 ohms, find the approximate change in the power if E is increased by 0.5 volt and R is decreased by 50 ohms. Okay. Yeah. Okay. You want to find the approximate change. Yeah. Mm. So here E is equal to 10 volt. R is given 2000 ohms. And what? E is increased by 0.5 volts. So assume that as delta E, 0.5. And R is decreased by 50 ohms. So assume that is delta R. Because it is decreased, you must use negative sign. Okay? Yeah. Because if it is increased, we use plus sign. If it is decreased, we use minus sign. So minus sign due to decrease. We use minus sign due to decrease. So we want to approximate, find the approximate change in the power. So that means we want to calculate P. Use the formula that we have discussed just now. It is using the appropriate symbol here. E is R plus delta R is approximately equal to P of ER plus delta P over delta E evaluated at ER times delta E plus delta P, P partial R evaluated at ER times delta R. Okay. Previously we used X, Y, A, B. Okay. So here we use variables ER. So you write down the formula according to the symbols in the what according to the, we need to change the symbols accordingly. Yeah. If we use XY, then we use a linear approximation formula in terms of XY. If we use others here in the ER, so we use the linear approximation formula in terms of ER. So what is P partial E? We need to determine P partial E and P partial R. So let's calculate E partial E first. So we treat R as a constant. What is P partial E? Anybody? Yes? What is P partial E? You should be an expert by now.
3e squared over square root
3e
r
squared, yes. 3e squared
over square root r.
over square root R. And what about the other partial derivative, P partial R? So now you want to treat E as a constant, right? we can also write this as e cubed times r to the power of minus a half. Okay, 1 over square root r is the same as r to the power of minus a half. So e is a constant. E is assumed constant. So we can pull out e cubed. So what is that? What is the derivative of r to the power of minus a half?
Negative 1 over 2 r negative 3 over 2.
Yes. This one, right? Yes. Yeah. So this is the same as minus e cubed over 2 r to the power of 3 over 2. Okay. So now we have found those two partial derivatives. So go back to the approximation formula. Therefore, P E plus delta E R plus delta R. Okay. PER, what is PER? E cube over R square root R plus P partial E is 3 E squared over square root R times delta E. Next we have P partial R, which is minus E cube over 2. R to the power of 3 over 2 is the same as R square root R, then times delta R, right? Okay. Okay, let's before we substitute the numbers, let's simplify this. Let's factor out e squared over square root R. So the first term in the bracket is e. The second term in the bracket is 3 delta E. And the last term in the bracket is what? E over 2R. E over 2R times delta R, right? Yeah. Okay, now we substitute. E plus delta E. What is E? E is 10. Delta E is 0.5. So this is 10.5. R plus delta R is R plus delta R. That means 2000 minus 50. 1950. E is what? 10. R is 2000. E is equal to 10. Delta E is what? Delta E is 0.5. E is 10. 2R. What is R? R is 2000. And delta R is minus 50. Okay. So simplify this. What do we get? You have 100. 10 squared is 100. 2000 is 220 times 100. Square root of 100 is 10. 3 times 0.5 is 1.5. Okay, what else? We can cancel 2 zeros downstairs. So that's what? Minus and minus give us plus. We have 5 over 4t, right? We have 5 over 4t, which is
1/8.
1 over 8. Yeah, 1 over 8. So if you use your calculator, what do you, can somebody tell me what is this value using your calculator? You can also 25.994.
994.
Yeah, that's also what I have. That's what also I got. Using your calculator is 225.994. Okay, so that is the approximate value using differentials. Any question? But we can, this is just, but we can calculate this exactly, right? Using calculator, the exact value. I can also calculate the exact value. Because we know the formula. The formula is what? What is the formula? Yeah.
E cube over square root R.
E cube. So that means E, this is E, this is R, right? This is R. Yeah. So E cube over square root R. E cube is 10.5 cube over square root of 1950. Okay, can somebody calculate this value?
26.22.
26.215.
215 lah.
Okay, okay. All right. So they're approximately close, isn't it? This is the approximate value, 25.95994 is the approximate. This is exact. This is exact. So it's reasonably close, isn't it? The value, the approximation is reasonably close to the exact value. Well, why we want to go through all the trouble, right? If we can calculate the exact value simply using calculator, why all the trouble, all this partial derivative stuff? Well, if you want to ask me that question, that is a good question. Yeah, but this is just to illustrate this how approximation, to illustrate the linear approximation formula here. Well, I asked that question myself, and there's a book. I found an interesting answer in one book here. Here. There's one book here, Mathematics for Physics, Chemistry. I sometimes also teach physics students and chemistry students. And here also, this book discusses applications of functions of several variables in chemistry, in physics. The pressure, okay, one example discussed here is the pressure. Consider a gas contained in a cylinder with a movable piston and a valve through which gas can be admitted or removed, and let the entire system be immersed in a constant temperature bath so that we can control the temperature. The pressure is a function of the amount of gas N, the temperature T, and the volume V. I think I have discussed this also in one example before. P is equal to N RT over V. Right? N is the amount of gas. T stands for temperature. V stands for volume, and R is some physical constant here. Yeah, R represents some physical constants. Yeah. So we can think of P as a function of three variables: N, T, and V. Right? Yeah. So here we are shown three partial derivatives of P with respect to V, T, and N. Yeah. Then one example is shown here. One example is shown here. Okay. It says here that the exact calculation. One calculation is for the approximation. The other is from the formula, from the exact formula here. So the above calculation made use of the partial derivatives, and this is the exact value, okay, from the formula given. So they are quite close. They are very close. They are quite close. Yeah, quite close. So in this example, the exact calculation could be made more easily than the approximation, yeah, isn't it? However, this is important. However, in physical chemistry, it is frequently the case that a representation of a function is not known, but values for the partial derivatives are available, so that approximation can be made while the exact calculation cannot. So there are cases where the exact formula is not known, but the experimental values of the partial derivatives can be obtained. So in such a case, the linear approximation formula is very useful to get a good estimate, right? Yeah. And he discussed this example here. For example, there is usually no simple formula giving the thermodynamic energy as a function of its independent variables. However, we can write this differential here. These partial derivatives can be obtained experimentally. So in some cases, the linear approximation formula is very useful, okay, for such cases where the exact formula is unknown. Okay, maybe I can copy that one and paste it here. I will give this in the e-learning also, right? This information, this application in chemistry. I will also upload this in the e-learning here. But I want to take a snapshot of this one here. Paste it here, yeah. Okay. Okay, next let's discuss the concept of differentials, which is also connected to linear approximation. Okay, recall that if x is close to a, then f of x is approximately equal to f of a plus f prime a times x minus a. If I replace x by a delta a, then the above approximation formula becomes to the second expression here. Now, if I take the difference, okay, the second expression is equivalent to the third expression here, right? And the expression on the left can be viewed as a difference of values of f, or change in f. may also mean small increment, or it may also means error. Yeah, error. The left expression, the difference is denoted by this delta F. Okay, this a triangle symbol here, delta F, to represent this difference. Okay, delta A is small quantity. Yeah, so A plus delta A is close to A if delta A is small. So this difference measures the error. Okay, the difference of values of F or change in F. Small increment. Yeah, because delta A is small, so we can think the difference as a small increment. Well, the expression on the right is F prime A delta A is denoted as dF. It is called differential or total differential. Yeah? So this means that delta F is approximately equal to dF. Okay, delta F may represent error, dF represents a differential or total differential. There is a terminology used in mathematics here. Yeah? So the same thing, the same idea for this function of differential for function of a single variable can be extended to a function of two variables here. For functions of two variables, then we have delta F approximately equal to, the error is approximately F partial x a b delta A plus F partial y a b times delta B. Okay, where what is delta F here for functions of two variables? It is F, the difference between F x plus A plus delta A. This x plus, no, A, I want A. It is A plus delta A, comma, B plus delta B minus F A B. Okay, the difference. Yeah. So similarly, the differential for functions of three variables, del F is approximately equal to the expression on the right-hand side there. Yeah. Where del F on the right means F, the difference between F A plus delta A, B plus delta B, C plus delta C minus F A B C. Okay, the error here. All right. So this below shows a table. It's various terminologies. So the error or small change or error in a small change of AB or ABC is represented by delta this delta F. Okay, the estimate is the DF, right? The differential here. Sometimes relative error is required to for certain calculation. You want the relative error. So the relative error is the exact relative error is delta F divided by FAB, while the approximate relative error is DF divided by FAB. And in the third row shows the percentage error. Okay, sometimes a percentage error is needed. So the exact percentage error is the relative error times 100%, and the approximate percentage error is the relative error times 100%. Okay, yeah. So So sometimes, during the test or final exam, sometimes change is required or error is required. Sometimes relative error is required, or sometimes a percentage error is required. Yeah. Okay, let's do another example. Yeah, this is sample test. This is a sample test one. Okay, we have this question here. Let's take this as our next example. This is also a sample test one. Yeah. In determining the specific gravity of an object, its weight in air is found to be A equal to 16.3 kilogram, and its weight in water is W equal to 9.1 kilogram, with a possible error in each measurement of 0.009 kilogram. Approximate the maximum error in calculating its specific gravity S, where S is equal to A over A minus W. Yeah. This is a problem related to physics. So we have an object with a known weight in air and with a known weight in water, and the specific gravity is related to A and W by the relation A over A minus W here. Yeah. Okay, here we are talking about error. Yeah, the question is related to error. So remember the table just now? The error here. And also percentage error? No, maximum error. We want the maximum error. Yeah, so that means we want to estimate the exact error using DF here. Using DF. So for a function of two variables, we need to use this formula here. This formula. Okay, so recall this formula. So here, the formula in terms of A, B, X, Y. So we need to apply this formula with the appropriate symbol here. S is a function of A and W, right? So S is a function of A and W. So we want, what is it that we want? What is given? A is given. Get the question, given A equal to 16.3, W is equal to 9.1. Okay, 0.009. What does that mean? Represents what? 0.009. What does it represent? We have 0.09 with a possible error in each measurement. So that means delta what? Delta A, delta W are equal to 0.009. Okay? Yeah. With a possible error in each measurement. Delta also measures error. So we want delta F, delta S is approximately to ds, right? Where ds is S partial A at what? A W times delta A plus S partial W evaluated at AW times delta W. Okay? So we use this formula with the appropriate symbol here. All right, it's 11:51. So, okay, let's have a 10 minutes break. We continue at around 12 o'clock, okay? So let's have a 10 minutes break. Okay, welcome back, everyone. Let's continue. Let's continue with this example. Maybe some of you have already solved this problem during the 10 minutes break. What answer did you get? If has anybody solved this problem during the 10 minutes break? Would you like to share your answer? Okay. Let's solve this. Let's continue. Okay, what is required here is S partial A and S partial W. Okay, look at the function S. We have S equal to AW equal to A over A minus W, right? So what is S partial A? You want this, yeah. This is the same as S using, this is also another symbol for S partial A. Curly D symbol, yeah. Has anybody tried this? We have A upstairs, also A downstairs. So let's try the quotient rule. That means we need to use the quotient rule. Okay, recall the quotient rule for the derivative or the function of single variable. The quotient rule is v times u prime minus u times v prime over v squared, right? Yeah. So that means we want v upstairs first times the partial derivative of the function upstairs minus the function upstairs times the partial derivative times partial a of the function downstairs divided by a minus w squared. Okay. So this is equal to what is this? What is a partial a? Anybody? Are you still with me?
Yes.
What is a partial a?
1.
1, yes. What about a minus w partial a?
1 also.
1 also. Yeah. So that means upstairs we have a minus w minus a, right? A minus w minus a is minus w upstairs. So divided by a minus w squared. Good. So that's S partial A. What about S partial W? So now we want to think of A as a constant. So this is, you can think of S written in the form of A times A minus W to the power of minus 1, right? And A is treated as constant, so I can pull it outside. Okay, what is this partial derivative equal to? Can use the chain rule. A times minus 1. The exterior, the outer function is the power function. Next, we differentiate the inner function with respect to W. And what is this equal to? So long. Simple partial.
-1.
-1. Okay. So we have minus 1 times minus 1. So that's A. That's 1. So we have A over A minus W squared. A minus W squared. So now, so therefore, going back to that approximation formula, delta S is approximately, okay? Notice that here I'm using approximation sign, okay? So please use the appropriate sign. Yeah. We have S partial A delta A. S partial A is minus W over A minus W squared times delta A followed by S partial W. S partial W is A over A minus W squared times by delta W. Yes. So this simplifies. Before substituting, let me factorize a minus w squared. So this is minus w times delta a plus a times delta w, right? But delta a and delta w are equal, isn't it? According to the question, delta a and delta w are equal. Yeah, so I can also replace this delta, two delta, no, this is a. Yeah, and this one is also equal to delta a. So I can factor out delta a also. So then I get, we have delta a over a minus w squared. We have minus w. If I factor out delta a, then I have minus w plus a, which is a minus w. So a minus w divided by a minus w squared is delta a over a minus w. Okay, now we can do the substitution. Okay, what is delta a? Delta A is equal to, according to the question, is 0.009. What is A? A is 16.3 minus W. W is 9.1. Okay, can somebody tell me what is the value using your calculator?
Mm, 1.25 milli.
Hmm?
1.25 times 10 to the power of negative 3.
Say that again. 1.25
25 times
times
10
10
to the power of 3. Negative 3.
negative 3. So that is 0.00125, right?
Yeah.
125. Now, is this correct? Look at the question again. Maximum error. Okay, the word maximum error is used here. Approximate the maximum error in calculating its specific gravity S. So the error, as you can see here, is approximately, this is the approximate error actually. What we have found here is actually the approximate error. If the question asks for the approximate error, then this is the answer. Okay? If the question asks for the approximate error, this is the answer. But the question asks for the maximum. What is it? The maximum error. Maximum error means we want to look at the absolute value. Okay, we want to look at the absolute value. The absolute value. Is approximately what is it? Yeah, look at this. Look at this expression here. Maximum error. A minus W. Yeah, then can be written in this form. Take the absolute value. And this is by the triangle inequality. Remember the triangle inequality? The modulus of say x plus y is less than or equal to modulus x plus the modulus y. Okay, this is what I want to use. Yeah, this is less than or equal to this one here, minus w a minus w squared delta a plus this one here. Yeah, this is what we need to apply when we look for the maximum error. Use the triangle inequality. So this becomes what? Minus the absolute value of minus is 1, right? The absolute value of minus 1 is 1. So we have w over a minus w squared delta a. And then we have also this one here. Okay? And delta A is equal to delta W is equal to delta A. So I can factor out delta A. So I can, upstairs we have W plus A divided by A minus W squared times delta A. So now we substitute. Okay. It's less than or equal to. What is W here? W is 9.1 and A is equal to 16.3. Downstairs we have 16.3 minus 9.1 squared and delta A is 0.009. Okay, can somebody calculate this value now using your calculator?
Four point four one multiplies 10 to the power of negative 3.
Okay, so this is 0.00441, right? Okay, so this is the actually the value required. It asks you for the maximum error. So what you have obtained earlier here is just the approximate error. So what is required? The maximum error. So that means this is the answer here for this question. That means the actual error can be no bigger or larger than this value. Any question for this example? Okay, so we have looked at one example related to error. We have also the maximum error, and then the relative error is also possible. What is the percentage error? Percentage error. What is the relative error? Yeah. This is the approximate error just now. And what is the relative error? Suppose you wish to know what is the relative error. Then according to the approximate relative error. According to the table, the approximate relative error is the error divided by FAB. Yeah, FAB. Yeah, the relative error is approximately equal to FAB. So for this problem, the delta S divided by S at, what is A? Here A 16.3, W is 9.1. We have already found delta S, right? Previously, it's 0.00125. 0.00125. What is S 16.39.1 equal to? Okay, that is what we need to calculate here. Is equal to A, yeah, so 16.3 is A, 9.1 is W. So if you substitute, you get what? 16.3 divided by A, 16.3 minus 9.1. Okay, can somebody calculate this one for me?
2.264.
2.264,
64.
okay. Okay, now can you calculate again this one? 0.0125 divided by 2.264.
0.00055.
This one? Okay, so that is the relative error. Okay, what about suppose we are interested in the percentage error. So then we need to use this formula. We just multiply the previous result by 100, isn't it? By 100. So the previous result, 0.00055 times 100%. That means 0.055%. Okay, that is the percentage error of the calculation. Okay, even though the question here did not ask for the relative error and the percentage error, but I just show you how the calculation looks like in case it is required. Okay, let's do one more example before we stop. Okay, let me choose another example related to electricity. The total resistance R for two components with resistances R1 and R2 connected in parallel is given by uh, 1 over R equal to 1 over R1 plus 1 over R2, isn't it? Yeah. If R1 is equal to 300 ohms with a percentage error, say 2%, and R2 is equal to 500 ohms with percentage error 3%, determine the percentage error for R. Okay, this is the question. Okay, we have 1 over R equal to 1 over R1 plus 1 over R2. Okay, we want to work with R, isn't it? So let's solve for R. So we first express 1 over R1 plus 1 over R2 as a single fraction. So upstairs we have R1 plus R2. So therefore, if we take the reciprocal, we get R equal to R1, R2 divided by R1 plus R2, okay? So R is a function of two variables here, R1 and R2. So what is given here? We are given the percentage error, isn't it, for R1 and the percentage error for R2. So we are given percentage error need to be written as delta R1 divided by R1 times 100% equal to 2%, right? 2% here. Yes. So that means delta R1 over R1 is equal to 0.002. It's the same as 2 over 100. And we're also given delta R2 over R2 times 100% is 3%, isn't it? And the percentage error for R2, so that means that is mathematically is delta R2 over R2. So therefore, delta R2 over R2 is 0.003. Yeah.
Doctor, may I
Yeah.
ask, is
Uh-huh.
it the delta R over R1 is equal to 0.02 only or 0.002?
Oh yeah, you're right. Yeah, thank you. Mata saya dah blur lah. Tengok skrin lama-lama ni. Okay, thank you for the correction. Yeah. Okay, what is it that we want? We want to approximate, isn't it? Delta R over R. This is what we want. So we want to approximate. Yeah. This is what we want. We want to find the approximate. Determine the approximate. I should. There's another word here. Approximate percentage error for R. Yeah, we want to approximate the percentage error for R. So this is what we want. So recall delta R is what? What is delta R? Going back to this formula again. Yeah. We want to apply this formula again. No, I'm sorry. Before that, the other formula. Which one is it? Yeah, this one. Copy. I didn't copy. Okay. You recall this formula. Yeah. Now, instead of F, we're going to use capital R. Instead of AB, we want to use, instead of X, we want to use R1. And instead of Y, we want to use R2. So delta R is approximately equal to R partial R1 times delta R1 plus R partial R2 times delta R2. Okay? Yeah. But so, and then we want to divide this by R, isn't it? You want to find the percentage error. That means you want to divide this by R. Yes. What is R? What is R? R is R1 plus R2 divided by R1 plus R2. Well, okay. Okay, let's calculate delta R partial R1 first. Okay, to calculate this, we need to know to calculate the percentage error, because the percentage error involves delta R. So that means we need to calculate delta R. And delta R involves partial derivatives of R1 and R2. Okay, you can also do this, yeah. There are several ways, you know. There are several ways, yeah. What is R? R is equal to what? R1, R2 divided by R1 plus R2, right? Okay, let me substitute this first. So R, the second term is also R1 plus R2 divided by R1 plus R2, okay? Yeah. Now I can rewrite delta R1 divided by bracket term as R1 plus R2 divided by R2 times delta R1 over R1. Because that is what is given, isn't it? Delta R1 over R1 is given, yeah. And for the second term, I can rewrite the second ratio as R1 plus R2 divided by R1 times delta R2 over R2. Why we want to write in this form? Because that is the information given here. Those are, because we have this information there. Yeah, we have that information. So this is equal to 0.02, while the second one is 0.03. Yeah, that's the reason for rewriting it in that form, because we have the value of these ratios here. So the next step is to find the partials. Okay, next step is to find the partials. And what is this thing equal to, and what is this thing equal to? What is R again? R is R1 times R2 divided by R1 plus R2. Yeah. What is this partial with respect to R1? Use the quotient rule again. Yeah, we need to use the quotient rule again. Okay. And the first partial here is equal to R2. The second partial here is equal to 1, right? Yes. So that simplifies to R1 plus R2 times R2 minus R1 R2 divided by R1 plus R2 squared. Okay, we can factor out this. We have a common factor here, R2. So what is that equal? If I factor out R2, then I have R1 plus R2 minus R1 divided by R1 plus R2 squared. So R1 cancel out here, right? So upstairs we have R1, we have R2 squared, yeah, over R1 plus R2 squared. Okay. Similarly, the result of R partial R2 is just interchange R1 and R2. Yeah, we just interchange R1 and R2. So we get R1 squared divided by R1 plus R2 squared. Okay. So now we substitute. So substituting where? Here in this equation. Substituting into equation star, then we have delta R over R approximately equal to, the first partial is what? R partial R1, which is R2 squared divided by R1 plus R2 squared times R1 plus R2 divided by R2 times 0.02. Then plus the next one is R1 squared over R1 plus R2 squared times what? Times R1 plus R2 divided by R1 divided by R1. Yeah, then times 0.03. Okay, so we can simplify this. 1 R2 cancel out and R1 R2 also cancel out. So that leaves what do we have? R2. What is it? Can factor out R1 plus R2 times, we have R2 times 0.02 plus R1 times 0.03. Okay. Now the next step is to substitute the values of R1, the given R1, R2. Yeah, this one here. The next step is to substitute these two values of R1 and R2. R1 is 300, R2 is 500. R1 is 300 and R2 is 500. It's the other way around. Should be 500 here, right? Times 300, 0.03. Okay, can somebody help me with this? And please simplify this. Mm,
0.024.
0.024.
1980, 800.
Or 2375, is it, to be more
Yeah,
precise?
2375.
Okay. Yeah, okay. So what is the percentage error? The percentage error, you need to multiply both sides by 100. So that gives 2.375%. Okay, that is the answer. The percentage error for R is 2.375%. Determine the approximate percentage error for R. You have any question here? Now compare this question with this one here. Nope, not this one. I changed the question slightly. Suppose now I change the question here slightly. Then I want you to think about it. Copy, copy. Yes. If the percentage error in measuring R1, if the percentage errors in measuring R1 and R2, they are both the same. Let's say 2%. Use partial derivatives to approximate the percentage error in calculating R. Okay, I will not solve this now, but I want you to think about it. What is the difference here compared to the previous question? The previous question, you're given R1, right? R1 300 ohms and R2 500 ohms. But now, in this question, that info, we don't have, not given any values for R1 and R2 anymore. But the percentage errors in measuring R1 and R2, they are equal. They are equal. In the previous example, they are not equal. The percentage error for R1 is 2%, the percentage error for R2 is 3%. So think about it. Okay? Think about it and let me know. Almost the same calculation is required in the previous example. Yeah. You see what happened if the percentages here are equal. If this is 0.02, this is also 0.02, I can factor out 0.02. Then we have R1 plus R2 that will cancel out with this R1 and R2, right? Yeah, I'm giving you a hint now. Yeah. So that's why in this example, you don't need no specific values for R1 and R2 are given. Yeah. Okay, that's all for today. So I'll see you next Sunday, yeah, for this what? For the makeup class, yeah, next Sunday 8 p.m. for the makeup class, right? I've already mentioned about that in the beginning of our lecture today. Where is it? Oh, I didn't write it here. Where did I read? Here, probably. Where did I've written it somewhere just now. Where has it gone? I've written just now, right?
Yes,
The
at PM. But
yeah,
I also don't remember where is it.
where did I
I
write?
take note later.
Okay. I remember I've written it down. Maybe
Sunday.
it's just still here. Maybe I've written it down here. Yeah, I've written it down here. Makeup
Yeah.
class, 11 April, Sunday, 8 p.m. Right? Okay, take note because next Tuesday is a public holiday for Johor State. So we have to do this makeup class. Yeah. Okay, next, let me show you the QR code for your attendance. All right, there you are.